Hello everyone. In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will focus in on the conservation laws of charge, baryon number, lepton number, and strangeness. Alright, so up to this point we have briefly gone over the different particles that constitute the standard model of particle physics. We've gone through sort of the different terminology that applies to particle interactions and the particular particles involved. Now, what do questions on this look like? Well, some questions on this will simply be asking sort of for the properties of the particles that we just discussed. But most of the questions will involve some kind of prediction, a prediction of the outcome of a particular interaction. So you'll be given a couple of particles that interact via one of the four major interactions and be asked, for example, to predict an outcome. Now, how do we do that? Well, as it turns out, there are a lot of questions that can be asked by simply paying attention to a whole bunch of conservation laws that apply to particles. Now, some of those we've already seen. We know that mass energy and momentum are conserved in particle interactions, and we have seen that charge is also conserved. But as it turns out, charge is just one of a number of quantum numbers. It's sort of a weird thing to say, but charge is just one type of quantum number that is conserved in particle interactions. And the main ones we're going to look at, so your go-to tools, will be charge, baryon number. Remember, baryon number is +1 for any baryon, and -1 for any antibaryon, and 0 for anything else. And that comes from each quark having a baryon number of +1/3, and every antiquark having a baryon number of -1/3. As it turns out, lepton number is also conserved, which means the total lepton number at the beginning must be the same as the total lepton number at the end. Recall that leptons have a +1 lepton number, and antileptons have a -1 lepton number. As it turns out, there's one more quantum number that is conserved among interactions, but not all of them. And I will also say there are more quantum numbers. This is the last one you need to know. And I will say, just as a teacher, it's a little bit odd that this is in the syllabus, in part because although it's very important historically, the sum total of what you're supposed to know about it is not particularly clarifying. But in any case, in non-weak interactions, so any interaction that is electromagnetic, strong, or gravitational, the property of strangeness is also conserved. Strangeness is simply defined as -1 for any strange quark and +1 for any anti-strange quark. This is backwards from the normal convention, and that is due to historical reasons. As I said, there's a huge amount of historical background tied up in this particular conservation law, which is why sort of the IB is expecting you to know it. On the other hand, we have so little access to that background, and you need to know so little else about it that it seems a little standalone, but just take it for what it is. Strangeness is -1 for any strange quark and +1 for any anti-strange quark. Note that in the data booklet, you are given much of this information, including that particular fact. So all quarks have a strangeness number of 0, except the strange quark, which has a strangeness number of -1. Add that to the fact that all antiparticles have opposite quantum numbers, and that fact is literally in the data booklet, should you forget it. You'll note that the rest of the standard model, organized a little sort of idiosyncratically, is also in your data booklet. So this whole chunk is in the data booklet. What might you be able to predict with this? Well, here's one example. All right. This particular particle, a delta naught, is composed of an up, down, down quarks. Oh, I should say this now. For all complex baryons and mesons, you are not expected to memorize their quark composition. The only exception are protons and neutrons. So even if you see example problems that expect it, they usually expect it because if they're in a textbook, there is a table somewhere in that textbook. In the actual exams, they will give you the composition of any particle you might need. In any case, this delta naught particle is composed of up, down, down, and it decays into a proton plus a negative pion. It has a lifetime of 10 to the negative 25 seconds, which is very short, and characteristic of the strong interaction. Strong interactions are very short range, but also happen very quickly, relatively speaking. Whereas the decay of the lambda naught particle, up-down strange, takes much longer. And although both of these seem like a fraction of a second, it is important to recognize that the up-down strange particle, our lambda naught particle, decays to the same products in 10 to the 15 times longer. So this is not a small difference. This is a massive, massive, massive difference in order of magnitude for the lifetime. And the reason that this is important is because it shows us that it has to decay, or it must be decaying via the weak interaction. The weak interaction takes a little longer to take place, by and large. And as a result, why is this? Well, it's because strangeness is conserved in the strong interaction, but not in the weak interaction. So while this particular particle, the delta naught, can decay according or using or with the strong interaction, our lambda naught particle cannot. It must wait to decay via the weak interaction. Notice that charge and baryon number, and quite straightforwardly lepton number as well, are conserved in the interaction. And when you're dealing with sort of these problems right here, so if you're given a prediction problem, they're pretty straightforward to identify as a conservation law problem because they'll give you some version of this and ask whether it's possible, or they'll ask you to fill in a particle. And a lot of the times what they're expecting you to do is simply run through charge, baryon number, lepton number, and strangeness, and check to see that they're conserved, or use their conservation to predict an outcome. So charge here, both of these charges are neutral. The proton has a +1 charge, the negative pion has a -1 charge, so that works out. And for baryon number, there's one baryon on the left and one baryon on the right. If you recall, that negative pion is a meson. In what follows, you'll see sort of examples of this. So you'll see sort of the type of question that you're going to get. And in particular, I would strongly recommend sort of taking a look at this sort of problem right here, which simply asks you to check the various conservation numbers and use the conservation laws to check that they're okay. You will also find sort of additional problems here. Take note, some of these problems are expecting you to have previous access to some quark composition, but most of them, as you can see right here, will give you the necessary quark composition in the statement of the problem.